Now we're going to talk about gravitational potential energy, one of the types of mechanical energy, but we'll review mechanical work a little bit before we start. So a student uses a force of 20 newtons to push a book 1 meter along a table. A frictional force of 20 newtons opposes the motion of the book. The work done by the student is... Now, the key here is work done by the student. If we're looking for the work done by the student, then we will only consider the force exerted by the student. The frictional force is of no importance. And we get 20 joules because work is equal to the force times the displacement. These are magnitudes times cosine theta. Here we're assuming that theta is 0, meaning that the direction of the force is the same as the direction of the displacement. So we have 20 newtons times 1 meter, and we get 20 joules. If a force is applied to an object that is opposite its direction of motion, the total mechanical energy of the object will be decreased. Because if the force is opposite to the direction of motion, that is the direction of displacement, it means that negative work is done on the object. In the previous example, the friction force would be doing negative work. So if in the first question we were asked what the total work was done on the object, we would have to include the negative work done by friction. Gravitational potential energy. This is one of the types of mechanical energy that we're going to talk about in the course. And not surprisingly, it exists because of the force of gravity. So you have gravitational potential energy right now. How much? Well, that depends on your height above a given point. So if we climb the stairs, which we'll do later in an inquiry activity, you will gain gravitational potential energy because your height above a given point has changed, has increased. If we want to lift an object through some distance called delta h, let's say, at a constant velocity, the applied force that does the work has to be equal in magnitude to the force of gravity, but it will be opposite in direction if we're lifting the object. In other words, the force that we use has to have the same magnitude as the weight of the object that we are lifting. And remember that work is equal to the magnitude of the force times the magnitude of the displacement of the object, as long as the force is in the same direction as the displacement. But in this case, if we're lifting the object with a constant velocity, the force is equal to m times g. There's the weight of our object. And the displacement, or the magnitude of the displacement, is just equal to the change in the object's height. So that's another way to write the work done on the object as we lift the object. The energy that this work increases is called the gravitational potential energy. So we can write gravitational potential energy this way. Although quite often we'll omit the deltas. So we'll often write gravitational potential energy this way. Eg equals m times g times h, where m is the mass of the object, which needs to be in kilograms usually. Height is measured in meters, as long as we are given the gravitational field strength in newtons per kilogram, which we usually are. Those are the units that we should use. H is the height of the object relative to some reference point. And we might be given the reference point in a problem, or we may have to choose it ourselves. If we're choosing the reference point, then we need to be consistent. I will often choose the lowest point in any given situation and use that as the reference point. But then I keep the same reference point throughout the problem unless the problem indicates that I should do otherwise. So that means that there's no magic spot or designated spot on Earth that is your reference point with zero height. Again, either we choose the reference point or a problem may give us the reference point. Let's try an example. We have an object of mass 3 kilograms and it's being lifted at a constant velocity from a height of 1 meter to a height of 2.5 meters. So that means relative to some reference point. We're not sure what the reference point is, but we're given the two heights that we need. Find the increase in the gravitational potential energy of the object. So we'll write down our given values first. So we've got our mass, we've got gravitational field strength, we've got our change in height, but we'll work that out. So we'll take 2.5 minus 1 meter and we get 1.5 meters, and our unknown is our gravitational potential energy. Now we'll select our equation. So we'll try our shiny new equation for gravitational potential energy, and then we'll substitute and solve with the values that we have. And we get 44 joules of energy. So that's an increase of 44 joules of gravitational potential energy, which is not much. Now we're going to try an inquiry activity in which you're going to change your gravitational potential energy, and then we'll do some practice.